First, I would like to thank the organizers to give me the opportunity to present my work here. So, today I will be talking on the dark matter halos of H1 selected galaxies. This work I have done with Nishi and Sandeep last year. So, this is the outline I will follow in this talk. So, I will briefly uh, discuss the objectives and the data we have used here, and then I will discuss about some the distribution of H1 properties in galaxies, and then I will be trying to relate H1 properties and halo properties using abundance matching. And what are the problems in doing abundance matching? I will discuss those and how we are overcoming that. That will also I will discuss, and then I will summarize. So we are convinced enough that neutral hydrogen is an important element to understand the our universe. So in this work, what we are trying to do, we have H1 neutral hydrogen, we have galaxies, we have halos. So what we are doing, we are using the link between H1 and galaxies and halos, and we are trying to linking H1 and halos using these two. Basically, we want to get the scaling relations between H1 properties and halo properties. And also, we would like to see whether these properties are different for different kind of populations or not. So, the data we are using here is from Alpha Alpha survey. Alpha Alpha is a blind local extragalactic H1 survey. So in this figure, this is the blue points are the Alpha Alpha galaxies in RA deck plane, and 98% of these galaxies have optical counterparts in SDSS DR7. These red patches are showing the SDSS footprint. Now, we are considering the galaxies which are common to both SDSS DR7 and Alpha Alpha, which has been denoted here using this black boundary. So, in our sample, we have around 7,800 galaxies, and if you look at this right panel, this is the two-dimensional distribution of these Alpha Alpha galaxies in W50 integrated flux plane. And this orange line is the 50% completeness limit. So we are considering only the galaxies which are above this limit. Now, the point here to be noted is that the underlying distribution of these galaxies are not only a function of the H1 flux or H1 mass, but this also depends on the parameter W50, the profile width. So, the underlying distribution is a bivariate distribution of H1 mass and W50. So we need to keep in mind while we will estimate the H1 distribution of H1. Now we want to estimate the H1 mass function, H1 width function, and H1 velocity function. So to do that, first I will start with the definition. So H1 mass function can be defined as the underlying number density of galaxies with H1 mass range between MH1 and MH1 plus DMH1. And this can be parameterized using a 3-parameter Schechter function like with this form, where phi star is the amplitude, alpha is the slope at the low mass end, and m star is the characteristic mass or knee mass. Similarly, we can define H1 width function, and this can be parameterized using a 4-parameter modified Schechter function, where this beta parameter is extra, which was 1 for this case. So now we have taken this 2-dimensional stepwise maximum likelihood method to estimate the joint or bivariate distribution of MH1 and W50. And this is what we get. So if you look at the lower panel, the pixels are the results from two-dimensional stepwise maximum likelihood method, and this gives the underlying distribution in that MH1 W50 bin. And we have overplotted the observed alpha galaxies as the orange dots here. Now, if you integrate this two-dimensional distribution over W50, you will get the H1 mass function, which is in the upper panel. And if you integrate over MH1, you will get the H1 width function, which is in the right panel. So now we can estimate H1 mass function, H1 width function, and now we want to get the distribution for the populations of galaxies. But for that, first we need to define our population, and that we will do using the color magnitude definition. So here I have plotted all the alpha galaxies as a function of U minus R color and MR. And this dashed line is the traditional separation between red and blue populations taken from Baldry et al., which is based on the SDSS galaxies. So we use this separator to define our population, and we estimate the H1 mass function and H1 width function, and these are the results. So in the left panel, these are the H1 mass function for total blue and red population, and in the right panel, these are the H1 width function for total blue and red population. So you can see here in the left panel that the blue population is dominating the total H1 mass function at the low mass end up to the knee of the mass function, whereas you can see that the high mass end of the H1 mass function is dominated by the red galaxies. And similar trend can be seen in the H1 width function case also, but here these distributions are well separated. Now we would also like to look at the distribution of the intrinsic rotational velocity, and that we will do, since we don't have the V rotational values, we will do it like this. So what we will do, first we assume that the H1 velocity functions will also have a parametric form, four parameter parametric form of like modified checker function. And what we will do, we will scan the parameter space, and we will pick a set of parameters. We will give random orientations to those, and we will estimate the distribution of W50, and we will compare this with our actual H1 width function, and using chi-square minimization, we will get the best fit parameters, which will give us the H1 velocity function. And these are the results which we get. So in the left panel, we have overplotted the H1 width function for the comparison purpose. And in the right panel, you can see the results for H1 velocity function for the total blue and red samples. So now we have all the distribution for H1 properties, and we will now try to relate these with halo properties. So abundance matching is a technique which we can use to do this, but the question is whether we can use abundance matching in our case. So abundance matching assumes that the properties we are trying to relate should have a monotonic relation. But do we have monotonic relation between, let's say, H1 mass and halo mass? So to answer that, if you look at here, these are the two-dimensional distribution of SDSS galaxies and alpha galaxies as a function of U minus R and MR. You can see here that around 11% of the optical galaxies have H1 counterparts in alpha, and around 36% of the blue galaxies have H1 detection here. And again, if you look at this range, the brighter side of this plot, this is dominated by the red galaxies. So we can see here that these bright red galaxies do not have considerable amount of H1 detection. Now, MR is strongly correlated with halo masses. So from here we can say that the massive halos will not have considerable amount of H1. Again, this fact has been supported by Atlas 3D project. So what they have done, they have targeted massive early type galaxies, and they have reported that the detection in the H1 detection in the early type galaxies are quite less compared to that in the late type galaxies. So we do not have a monotonic relation between H1 mass and halo mass. Now, if we plot our alpha galaxies as a in the MH1 M star plane, so these are the 0.5 and 1 sigma contour of that distribution, and these black stars are the bend values for this, and these green points are taken from Huang et al., which is also for alpha samples. Here you can see that this shows a correlation between MH1 and M star. But again, if you see, look at these pink points taken from Catenella 2013, you cannot see any correlation. And that is because this sample has been selected, that sample is scalar mass selected. So, we can say here that for an H1 selected sample, the H1 mass and scalar mass are correlated. So, since M star, scalar mass and halo mass are correlated, we can say that for an H1 selected sample, H1 mass and halo mass have correlation. So, what we have to do, all we have to do is to define an H1 selected halo mass function. So here the thick black line in the right side plot is the halo mass function taken from MDPL2 multi-dark Plankton simulation, and if you use this halo mass function and our H1 mass function and do abundance matching, you will get this blue line in the left plot. Sorry, this dashed black line in the left plot. And these red circles are taken from Guo et al. 2020. These are the mean H1 mass halo mass average H1 mass halo mass relation based for the alpha galaxies based on stacking analysis. So since we have argued that we cannot do the abundance matching with the total halo mass function, we need to define one H1 selected halo mass function. So we will do that in such a way that the H1 selected halo mass function and our H1 mass function, if we do the abundance matching and we do the averaging for the total halo mass number of halos, that will match with these red circles. So we have done that using this parametric form. So here this has three parameters: F, gamma, and MH star. So F is the fraction of halos which will host H1, and gamma is the suppression at the high mass end, and MH star is the threshold value of halo mass after which that suppression will happen. So we have seen that with these parameters we get our desired H1 selected halo mass function, and if we do the abundance matching, this is the scaling relation between H1 mass and halo mass for a H1 selected sample, and that can be parameterized using a double power law where MH1A is the amplitude, alpha is the slope at the low mass end, which will suppress to alpha minus beta at the higher masses, where the transition halo mass in log is this. Now we want to do the same thing for the red and blue populations also, But here we have considered the analytical galaxy evolution model SAGE, which is calibrated using the scalar mass function. But SAGE does not give the color magnitude properties accurately. So we have to take some alternative definition of the population, and that we have taken age. So if you look at this figure, you can see that below 8.34 giga-year age, the distribution is dominated by the blue galaxies, and above that, it is dominated by the red. So we have taken this definition, and we have estimated the stellar mass function for late type and early type galaxies, and you can see that the late type distribution is dominated at the low stellar mass values, and early type is dominating the higher masses, which is the typical bimodal stellar mass we have in our mind. So we have now we have the definition for populations. We have defined the H1 selected halo mass function using the same expression for late type and early type also, and we have estimated the scaling relations. So these are the scaling relations for this is the left side is the scaling relation for H1 mass halo mass. Then this is W50 and halo mass, and this is rotational velocity and halo mass. What you can see here that the gas-rich galaxies typically have similar kind of scaling relation for red and blue populations, but the gas-poor galaxies, in case of gas-poor galaxies, the relations are different. To end, I will summarize this talk with a consistency check. So what we have done, so we have considered a volume limited sample from alpha, and we have mapped the H1 masses to halo masses, and we overplotted those with the scaling relations we have just estimated. So here in this figure, the dashed line is the scaling relation with estimated from the abundance matching of the total halo mass function and H1 mass function, and the solid line is for the H1 selected halo mass function and H1 mass function. So it is clear from here that we should not use the total halo mass function to do this to estimate this scaling relation. We should consider the H1 selected halo mass function. Thank you.
Nice talk. So it's open for questions. This is really nice. So I was wondering, have you compared your H1 mass function with these fancy galaxy formation simulations, which people have now done, Eagle, Illustris, that sort of stuff?
Yeah, we have not yet done, but we will do that.
That would be very interesting.
Yeah.
Thank you.
Zero session.
Whereas, is that correct that that one of the sample the change from W50 to 0 the mass function looks same, whereas the other one is showing some significant change? Is there any way of understanding why it is happening?
So actually the shape is not changing, but everything is just squeezing.
Okay, maybe I'm reading it wrong. See that dash dot line,
Yeah.
which is the Zuan thing, that has a shift of that has a change in the shape there also, whereas your
so actually this is from the previous work, so they have some other selection effects, that's why that is not matching with our. But if you consider this dotted line from Papa's service, this is for the alpha sample, and this is for the blue sample. So that you can see with that is comparable here.
Okay. Okay.
Any other questions?
So they does not give us the color magnitude values in the Halo catalog.
No, Sage doesn't do that.
No.
No, but you have to run another code.
Yeah. So for now we have
Okay.
just defined pick another definition.